My name is Larry Marvel. I come from the installation side of the floor covering industry, and I'm currently working as a technical rep on the installation side for a floor covering manufacturer. Being in this industry for 45 plus years on the installation side, this is one of the most important tools to have come along in a while that an installer could have at the start of their installation. You will hear information you might not have heard before, and why it's so critical to have a tool like this at the time of installation. As you know, everything evolves through science and through knowledge and understanding, and we have come a long way in moisture testing substrates, all the way back from late 70s and 80s when I watched installers testing for moisture in substrates with duct tape and plastic, to MVER testing, to RH, relative humidity testing, in situ type testing. And so today you're going to hear some new science and an evolution to testing in today's installation market. It's probably one of the most valuable tools right now you could probably invest in your installation management team or on your installation side. At the time of installation is when it matters. It's when you're preparing a substrate to install, most of the time, some very expensive product that you hope to last 10 to 30 years. And that adhesive has to bond and has to cure. What your challenges will be on the bond and the curing of those adhesives have to do with ambient temperatures, has to do with surface moisture in your substrate, has to do with dew point and slab temperatures. This is all information that we have at the palm of our hand within a few minutes at the start of your installation. And that's really when it matters. These simple tests can keep you away from a multitude of claims. What I wanted to do is introduce you to this video, ask you to take the time to listen to them, and as installers, as management of installers, those who manage especially large commercial sites where you can take control of your environment and let everyone know these things have to happen prior to the spreading of your adhesive, prior to the installation of that product. And it doesn't take days, it doesn't take weeks. You don't have to do this testing 72 hours prior. It gives you instant time of installation readings, which is most critical. That's when you need it. And it gives you the moisture at the surface of what you're installing on, which is what you need. That information is most critical for bond and cure. Thanks for taking time out. Listen to Bob Higgins and David Daniels. They're great guys, and we'll talk soon.
Hi, I'm Bob Higgins. I'm an independent concrete consultant, and I'm here to explain what installers need to do to make sure they protect themselves, not only their company and the installation, but the companies that they represent and they install for. One of my favorite examples of how profound condensation can be and why you need to be concerned with ambient conditions, I like to use the example of basketball courts. There's been several NBA games that they've had to cancel because moisture would collect onto the playing surface and became too dangerous to play on. One good example is the slide that you're seeing, and in this slide, it shows them mopping the floor, and what you don't see, there's fans off to the side. But every time they stop mopping and stop using the fan, the moisture would accumulate on the surface again to the point where they had to cancel the basketball game and postpone it to a later date. How this happened is this parquet floor is over a hockey rink, and it's cold. It's over ice. But any cold surface will do this, because this happens even in the high school and college levels where they don't have ice rinks. All it has to do is be cold, and much colder than the air. And when the surface is cold, that's, again, moisture moves from warm to cool. But as people kept coming into this stadium, and more moisture was available just from people breathing, they could not dry the surface. Now imagine if you go to a job site and there's been dozens of workers going in and out, open and closed doors, open and closed windows, the HVAC system isn't on. How much moisture do you think has accumulated in the concrete since the qualification test? We don't know. However, I want to really put in perspective just how much more moisture can accumulate, especially when you're talking about liquid water versus water vapor. For whatever reason, there's been this emphasis towards measuring the water vapor, which is relative humidity. That is a minute amount of the moisture that's in concrete. It's also such a small amount of moisture that they would have no effect at all on adhesive or the flooring materials as installed. This next slide, I like to use this because it shows 1 cubic meter of space. Now, if you took all the small pores and the holes that are in concrete, cracks, everything else, that's what's represented with an open space. Because if you're measuring relative humidity, that's what you're measuring. You're measuring open space. You are not measuring the solid. You're not measuring the concrete. You're not measuring the liquid water. You're measuring the open space and the moisture that can accumulate in there. Now, if you take a cubic meter of space and you want to fill it with water, it takes slightly more than 264 gallons of water. Now, if you want to get it to 100% relative humidity, it takes slightly less than 2 ounces of water. That's the difference. So, does that mean that 2 ounces of water in this amount of space is going to cause a flooring failure? That's ridiculous. Now, the other problem with many of these studies, especially in the test methods, RH probes measure 2 inches into the concrete. Believe it or not, that actually bypasses the problem area, and the data that you're receiving is of limited, if possibly even misleading value. Because the top surface of the concrete tends to dry out too early. Unknown to most, and was unknown to me until a few years back, was that the concrete, as it's curing, tends to do what's called self-desiccate, where it dries out too early and there's not enough formation of the cement. And with that, you end up with a much more porous and much more permeable concrete. So if you look at the slide, at the top surface of the blue arrow, that's the airspace above it. Now, as you go into the first section of the concrete, is very obviously porous, and there's a lot of holes in there. It's also more permeable, which can't be shown. And then the body of the concrete, where the RH probe would go in, it's in great condition. And we're taught, unfortunately, to believe that the concrete is monolithic and consistent all the way through. That isn't true. So the receptive area is the surface of the concrete. It's more permeable, it's more porous. There can be more water that's accumulated in the surface than anywhere else in the concrete. Now this slide is wonderful because it shows condensation on 3 different surfaces. The first slide that you see, there's condensation that's occurring along this wall. The second one is the common condensation you will see if it's hot and humid outside and it's air conditioned in the building, you're going to get that kind of condensation. You can write your name on it. Then the third one is a parking lot where I had to pull over and stop and take the picture because that was pronounced. So I'm going to work from the right side to the left side. That parking lot, it was very cloudy, it was very humid, and there's a lot of fog. Well, when the fog lifted, the moisture you see in the background was over a recently paved area that was nice and smooth. It had the nice smooth resurfacing that was done on it, whereas in the foreground, that's the older parking lot, and it's more porous and more permeable. So all the moisture you're seeing in the background that's soaked into that pavement in the foreground, that's what can happen to your concrete floor. So all the water you're seeing in the background that's not visible in the foreground, there's no less water there than there is in the background. Now the condensation that you see on the glass, how do you get rid of that if you're in your car? You turn on your defroster, and you blow warm air on it. So what does the warm air do? It evaporates the water. Again, water moves from warm to cool. I can't emphasize that enough, which is really emphasized in the slide on the left. The slide on the left, I was hired by a company, a very large manufacturer of epoxy flooring materials to come in and try to assess where this moisture was coming from. They did a leak location and they were doing all kinds of inspection. They could not figure it out. So I came in and ironically, with the same devices you use for the quick check, I came in with the infrared thermometer and I scanned along the floor. I went from the right side to the left side. The temperature of the concrete was 72 degrees. When I got over to where the water was condensing, the concrete temperature was 55 degrees. I said, well, you have a poorly insulated refrigerator and it's basically allowing the concrete to get cold. I said, well, how do we fix it? I said, well, you separate the concrete from the cold. So what I had them do is they did a saw cut right along the edge there, 3/4 of an inch down, because that is your gradient portion of the concrete. The first inch is the most important portion of the concrete. But once you get past 3/4 of an inch, you're not going to get the transmission, you're not going to get the lateral movement that you would otherwise. So they cut in, they put an insulative caulk and took care of the problem. And they were stunned that it was that easy to fix. But if they understood how moisture moves, they could have dealt with this on the front end. Now the concrete we're given is based strictly on its load-bearing capacity. It's not based on its ability to successfully install a floor. That's never even considered when concrete's being designed. Even though there's the ACI 302 that's supposed to be designed specifically for flooring materials, it really does fall short. Because again, what's being considered when concrete's first being placed and how it's cured is never considered in any of these specifications. So I love this slide here because if you look, the colder the environment when concrete is placed, the better quality of the concrete you get. However, if it's too cold, they don't get their 28-day strength marks, and that's what's evaluated on. So all concrete today is being specified based on the 28-day strengths, not anything else, not how durable it is, or anything of that matter. The second one shows 73 degrees Fahrenheit. That's considered optimal because at 28 days, which is represented by the blue graphic, that's your 28 days, it's 100%. And the orange graphic you see on the right-hand side, that represents the strength gain after 365 days. But if you notice, as the temperatures increase during the ambient conditions as concrete's being placed, the concrete strength gains much quicker and much more pronounced within 28 days, but the long-term durability and the long-term strength of the concrete suffers. So the warmer it gets, the better it is for the project as far as speed goes, but the worse it is for a floor. One of the problems we're running into, and it's a modern problem, I was doing some research on why concrete seemed to be getting worse, and I stumbled across an EPA edict where they're requiring the recovery of flue gases because that lowers the carbon footprint of the cement producers. So in the United States, they started this right around 2002 and it continued through till 2018. At that point, all the major cement producers were in compliance with the EPA regulations. Part of this regulation was to add what's called cement kiln dust back into the cement. This has increased the alkalinity of the cement dramatically, and this has not been conveyed to anyone in the industry, either specifiers, flooring manufacturers, installers. That's not conveyed to anyone. And alkalinity, it affects not only the drying, but it also accelerates the desiccation effect that you see in the surface of the concrete that they're experiencing on a global scale at this point, whereas it's getting much worse. What we're seeing also, as they're following all the procedures, and even those that are trying to be really careful, even the most conscientious specifier or installer who is ever responsible for the concrete, no matter how long they cure that concrete, they're not getting the product that they used to get. You can't do it at this point. So what's happening is we have a much more pronounced issue. So much more care needs to be taken when you're doing moisture testing. Now the alkalinity will interfere with any moisture test that's based on humidity or what's called desiccation extraction. The humidity is the hood test and the very common F2170, which is a humidity probe. Now the humidity probe unfortunately bypasses the area of concern, which is the first inch of the concrete. It goes well into the concrete where the concrete appears to be normal. And the readings you get have nothing to do with what the floor is going to be experiencing. And the calcium chloride test is a desiccant. It attracts moisture. Unfortunately, because the concrete has higher alkalinity, this higher alkalinity is a much more aggressive desiccant than the calcium chloride used. So what happens is they basically are fighting each other. So the free evaporation that would normally happen with a high quality, low alkaline concrete cannot be extracted using the calcium chloride test. So you cannot get what would be an accurate number from either one of those procedures, which is why I like the Tramex meter. The Tramex meter will evaluate the top 3/4 of an inch of the concrete and give you an exact number. Now this is how dramatic alkalinity is. The amount of measurable water vapor and the extractable amount of moisture is really predicated on how much alkalinity there is and has nothing to do with the volume of the water. If the alkalinity, say, is 20% concentration, it will bring the relative humidity down to 78%, even if the concrete is saturated with water. If it gets to 30%, it can go down to 63%. Now these numbers are important because when concrete is first being placed, the relative humidity in the concrete has to be above 80% to form cement. That's why this self-desiccation is so critical. So if you're getting less cement development, that's what causes your increase in porosity and permeability, because you're not getting the cement that you need, and that's what you're not getting in your design. And what the alkalinity does is it can attract moisture from the air, absorb it, and actually block any changes that may occur below that. So if you're doing an RH probe and you drill past the problem area, this area isn't going to show the alkalinity. It can't, because the alkalinity is accumulating towards the surface of the concrete. And this gets worse and worse and worse as the concrete ages. In conclusion, what constitutes dry concrete? Well, first off, there is no such thing. What we have to do is we have to rethink of how we're approaching what we consider and how we measure dry concrete, because the methods being used right now can't tell you if the concrete's dry or not. It can't do it. And what makes this even worse is we've been told that the older the concrete, the drier it gets, and that's true, but the problem is with older concrete, alkalinity tends to start accumulating towards the surface. So installers are constantly surprised and irritated that they will remove a successfully installed floor because they want to upgrade their image or just change the floor for whatever reason. Then they install a new floor and that new floor fails. And then they try to blame it on the moisture in the concrete. When actually it's the accumulated salts that are in the surface of the concrete. Recently we met with a group of installers, and they were really complaining and frustrated. They didn't know what to do with older concrete because, like they conveyed to me, that the older concrete was supposed to be easier and safer to install on, and they have way more problems on older concrete than they do newer concrete. Now, what's really interesting is they went back to the same group about 4 months later, and they were showing how to use the Tramex meter. And even though the warehouse is cold, is out of spec as far as where you can safely install a floor or meets the criteria as outlined by the manufacturers, they went ahead and did the moisture test on the concrete. It was 1.9%. Well, they ground down and they removed the curing compound. They did the moisture test. Once again, it was 1.9%. They walked away, and not 15 minutes later, they went back to the same area. They put the meter down, it was 4.3%. And they were absolutely shocked that the moisture level could jump up that much. And my explanation to them was the same. I said, that's the accumulation of salts. That's drawing the moisture from the air. More than 90% of the problems we run into is caused by ambient conditions. The measuring devices they're using and the testing devices they're using now cannot account for that. They're blind to this dynamic. The only thing you can use is the Tramex meter. So with concrete, it is the top inch of the surface that is your concern. Underneath the concrete isn't a big concern, and I've been told, so well, everybody knows that moisture migrates from the bottom up. I said, well, what everybody thinks they know is wrong. Because under most circumstances, and even how we're taught, the bottom side of the concrete's coolest. That's exposed to a cooler subgrade. As you get towards the surface of the concrete, warms up because of the ambient room conditions, and the ambient air is typically warmer than the surface of the concrete. Again, water moves from warm to cool. The concrete's drawing it in, it's drawn in deeply because it continuously gets cooler as it gets towards the bottom of the concrete. But water being what it is, as it gets into this permeable layer and it's got all the alkalinity in it, it actually locks in the moisture underneath, and you're not going to get a passable RH reading and seemingly contradictory. You're probably going to get a low calcium chloride reading, or it can even reverse on you. But what's happening is you're just getting bad information. The only way you can do this is using a Tramex meter.
Hi, I'm David from Tramex Meters, and today I'm going to introduce you to the tools and technique that make moisture testing of concrete slabs simple. The best way to test moisture in any material is gravimetric, which involves taking a piece of a material and doing an oven test in a laboratory. Now, obviously, this isn't practical or possible with concrete slabs, but Tramex has a meter for that. The CMEX5 is calibrated based on gravimetric testing. So just by a simple push to the surface of the concrete slab, you're going to get a percentage moisture content, which is the liquid moisture in the top 3/4 inch of the slab. And this area is crucial because it's the area that's going to act with your floor covering. So we always say to know your percentage moisture content or your liquid moisture content in the top 3/4 of the slab, because that's going to influence the bond line. You can see on this slide here, this is a study that was done by the VTT in Finland, where they were analyzing the best way to moisture test concrete bridge decks. So what they did in this study is they analyzed 4 different test methods, each one on polished concrete and on clean bare concrete. Now you can see the width of the black bar is the variance in repeatability of the test. So obviously how tight the results were over repeated tests. Now you can see here that the oven test or the gravimetric test on the bottom obviously has a very tight black bar, and you can see that Tramex is lining up almost exactly with that. And even there's 2 line items for each method. The top one is showing the method on polished concrete, the bottom one on clean bare concrete. So you can see obviously the clean bare concrete is what's ideal, and it gives you the best comparison to gravimetric testing with the CMEX5 in the field. The time of install kit contains all the equipment that you need to conduct an easy 3-step test to instantly and accurately evaluate the moisture condition of the concrete slab that you're about to install a floor covering on. So the first step of this test is to look at the ambient conditions. Now the nice thing is that the CMEX5 has a built-in hygrometer at the top of the meter, which gives you the ambient conditions across the bottom of the screen at all times. So what we want to note here specifically is the ambient dew point. So now that we've noted the ambient dew point, the second step of the test is to utilize the infrared thermometer. Now with the infrared thermometer, we're going to shoot the surface temperature of the slab, and we're going to note that in comparison with the ambient dew point. And we're just making sure that the surface temperature of the slab is at least 10 degrees Fahrenheit above that ambient dew point, or 5 degrees Celsius. Again, making sure the surface temperature is at least 10 degrees Fahrenheit above that ambient dew point. The reason this is important is because this is the condensation process with a concrete slab. So oftentimes people tend to consider that when a concrete slab is dry, it's dry. But we have to understand that concrete moisture is variable. So this is why with the different ASTM testing methods, they all say that the test results are good at the time of the test. And this is because moisture conditions in a concrete slab can change fast. Now we heard Bob give an example about a time that I was doing a demonstration with some installers, and we saw the moisture content go up more than 3% in less than 15 minutes. So this is a good example of how fast moisture conditions can change and the need for testing while you're installing. And what this is doing, this check here for dew point, it's just protecting against the moisture that can be drawn into the slab. We know that moisture moves from hot to cold, as Bob was telling us earlier. So generally a concrete slab is 1 to 2 degrees cooler than the air anyway. But what happens a lot of times, especially in situations where there's no HVAC. So say if you're installing in a situation where there's no HVAC and you have a cool night and the slab gets cold. In the morning, as the temperature rises, the slab will take longer to warm up than the air. And this is a very crucial time where you can encounter this dew point issue that will lead to failures. If you're not checking for this dew point issue and you simply install on top of it, you're trapping moisture up in the top portion of the slab. Now the good thing is the next step we're going to get into with the meter, that reading is going to tell us if we have high moisture. Now the strength of this meter is that it's going to pick up moisture wherever it came from. So while it's analyzing the top 3/4 of the slab, it's looking at liquid moisture content. Now whether that liquid moisture is already in the slab or whether it was pulled from ambient condition and has condensed in the top of the slab, it'll be indicated by a high reading on the meter. Now generally 4% is considered the dry number with a concrete slab. So if you're seeing elevated numbers, the question is why? We've conducted already the first 2 steps of this test, so we'll know if we have a dew point issue. If you don't have a dew point issue, a 4% or less reading on the meter is going to indicate that it's okay to proceed with installation. Now the way we're going to execute taking these readings is we're going to take 8 readings in the first 1,000 square feet with the meter, and then 5 readings in each additional 1,000 square feet of your space. And we're always going to note the highest reading. And the way we take these readings for each location is I'm going to follow around the clock method. So we take a reading 12 o'clock, 3 o'clock, 6 o'clock, 9 o'clock, and then I'm going to record the highest number as my first reading and go to the next location. So now after carrying out the readings with my meter and noting the highest reading in each location, along with the previous data that I have of the ambient dew point and the surface temperature, we're going to take a look at the moisture content numbers. We're going to take a look at and see if we have a dew point issue. Now, if I do have a dew point issue that's creating my high moisture content numbers, the next step that you need to do is to implement fans to create air movement. Now in this case where you get dew point issues, air movement's going to be your best friend, as long as the air can hold the water. So that's one consideration you have to start with. If it's a situation, again, where it's a morning install, the slab was cold from the night before and it's warming up, then generally air movement across that slab will be enough to bring that moisture content down, and you'll start to see those numbers come down within an hour or so. And once the numbers come down to around 4%, and again cross-checking surface temperature with ambient dew point to make sure you don't have that issue anymore, then you can proceed with your installation. If after running the fans for about an hour or so and you don't see the moisture content numbers start to come down and you still cite that dew point issue, maybe a sign that you need to run dehumidifiers to pull some of the moisture out of the air, so that moisture that you're pulling out of the slab with fans will have a place to go. Now, if you still are getting high moisture content numbers, but you don't cite that dew point issue anymore, it may be a sign that the concrete has further issues that you need to mitigate. The CME X5 is also great for moisture testing gypsum and cementitious screeds. The meter has 2 scales available in the non-destructive test options in the menu. The first one shown here is the CM on hydrite scale for gypsum. This one you'll see referenced in different gypsum manufacturer guidelines. It uses the 0.5% generally as the dry number. So 0.5% and less as dry. Generally up to 1% is considered in the caution zone. Above 1% is wet. So you just want to, when using this scale, make sure that you're cognizant of the 0.5. So it's 0.5 and not 5, because I've seen that mistake made before and it's definitely detrimental. So again, 0.5 is your dry number in this scale. Now there's another scale for gypsum. It's the Tramex gypsum scale. This one you won't see referenced by too many manufacturers, but it's easy for you to use because it uses the same guidelines as concrete, where 4% or less is going to be your dry number. So anything below 4% is dry. Above 4% you're going to consider still wet and need some more time to dry out. Now keep in mind, gypsum is different than concrete in that it dries out completely. So concrete is always holding some water, which varies according to ambient conditions and age. Gypsum is a material that dries out completely, so it's important to have an accurate test before installing. Another benefit of the CME X5 is it has Bluetooth connectivity, which will link to the Tramex Meters app. And with this app, it makes it really easy to document the testing you've done. So as you go into a job site, you can create a file for that job. You can designate different floors that you're going to test and create a moisture map where you're actually just tapping the readings as you take them to store in the map. You can geotag your test results, and all of this information can be saved so that in the future, if a moisture issue does arise, you have data from time of install to show the actual moisture conditions. The mapping feature is great because it allows you to control the grid size. You can actually overlay this grid over a floor plan to show specific places that the testing was done. I even had one super excited installer who flew a drone up into the ceiling to take a picture of the floor and then superimpose this grid over that picture of the floor to be super accurate. Now obviously everybody's not going to do that, but the grid itself just makes it real easy to see where your testing was done and to record those numbers just with a tap and save them. And this is just, again, making data and a file folder that's going to back the moisture testing that you've done and protect you should any failure arise in the future. Another thing you can do with the app is to verify calibration before you begin a moisture test. So what I recommend is that as you reach the job site, you're going to take out the calibration check plate that's included in the kit and put the meter on top of the check plate to verify calibration, and then turn on the Tramex Meters app and take a picture with a geotag of that reading, which will indicate the date, the place, and the time, as well as the verification of calibration of your meter. And this again is just another way to protect you should the need arise in the future. This kit gives you what you need to instantly and accurately understand the moisture condition of the concrete slab and have a successful flooring installation.